Hello everybody. Let us start our discussion today. So we'll bring tensors today to more general coordinate systems and let us see where we can go today. Before we go there, let me remind you of a few things which will again and again come back to. One is obviously how are we writing vectors first. So vectors, remember, these are also tensors of this type. We are denoting a vector by bar below the sign, and then we say that if there is a coordinate system S, it has as many components which are all some functions of the coordinates as the number of coordinates, number of dimensions. We also said that this I can write once I have chosen a coordinate system and basis for the coordinate system. I can write it in terms of the components along this basis in the following way. Okay, so let me remind you that these are the basis vectors. In the reference frame, in the coordinate system S, and these are the components. In the same coordinate system, of course. And sometimes we also call this, let me write that with a different color, covariant components. Vectors or the covariant components are written with a upstairs index. Now, before we go any further, here are two important points about the unit vectors or the basis vectors. So, basis vectors. So, the basis vectors, as we have leveled, the alpha-th basis vector. So, this alpha is, remember, it's not an index. This is the alpha-th basis vector. This is not an index. So, this is important to understand. This is not an index. This index is down, whatever it is, it's downstairs. So for a vector, I will not write an index downstairs. It is not an index. The second point is that to construct basis vectors, we just need d linearly independent vectors in a d-dimensional vector space. right? So it is not necessary that these vectors has to be a very special type. Any d linearly independent vectors in a d-dimensional vector space will form a set of basis vectors. However, we are not choosing any basis vectors. We will consider in this almost entire discussion only coordinate basis vectors. What are these coordinate basis vectors? Well, for each coordinates, there is one and only one basis vector. There is nothing as mixed up. For example, 2D Cartesian, so this is an example. Let me keep it here. So 2D Cartesian, I can choose my basis vectors to be, say, E1 to be x cap and E2 to y cap. This is the usual choice, right? So these are coordinate basis because I've chosen the basis in accordance to my coordinate. On the other hand, I can as well choose E1 as, say, x plus y and E2 as x minus y. And you can show that these are linearly independent. They also serves as basis vectors, but they are not coordinate basis. They are non-coordinate basis. Well, I can do a coordinate transformation. I can do a rotation where they will become coordinate basis. But if my coordinates are x and y, these E1 and E2 are not coordinate basis. So we'll only stick to coordinate basis vectors. The other important fact is that basis vectors, and this is where we will start our discussion later today, that basis vectors as we saw are like, I will write with an example. Say the E0 was having four components, all the basis vectors, because we are dealing with 4 dimension here, we'll have four components, and the four components are 1, 0, 0, 0. These are special basis vectors. Here, these basis vectors has same components at all coordinates, at all values of the coordinate. So let me write it as x alpha. Okay. These are constant basis vectors. Constant means that doesn't change as you move at different points or as you go from one event to the other. However, in general, without loss of any generality, we can have basis vectors those changes as the coordinate changes. So the basis vector values will change with the coordinates. And a simple example is the polar coordinates, where you know that the basis vector direction and the value both changes. We will see this in action in the next class as an example of what we will develop today. Okay, so this is the example of this point. Okay, so this is all about the vectors, basis vectors. Let me put in one more point here, that vectors are mapping from one forms to scalars. Remember that vectors maps, this we saw last time, one forms to scalars. Okay, so let me again highlight this with this color. Okay, so this is all about that we have learned, the gist of what you have learned about vectors. Now let us also look at one forms. So we'll go through all that you have learned and we'll highlight the caveats as we have done already for the basis vectors, and then we will generalize things. So one forms, they are tensor of this form 0, 1 now. We denoted them with a tilde upstairs. In any coordinate systems, they will have components which we'll write with downstairs indices. And the one forms can be written in terms of their components, and you will need the one form basis. So these are basis one forms. These are components in the coordinate system S, and this is essentially the one forms. One forms are, these are mapping from a vector to a scalar. So if I put in a vector in one form, it will give me a scalar. And let's see the one form operations. The operations we have done many times now. So one form takes the vector A, that essentially means that this will take the vector A can have component. You can write in terms of it components like this, and that will give me A alpha and P alpha, where we have used two things. One is that the definition of P alpha is the one form taking the unit vector E alpha, and also the unit one form W alpha takes the unit vector E beta, that is essentially delta alpha beta. So this is operations of one form on vector. Similarly, we have operation of vector on one form, that if you remember, I can write this as P alpha, and then unit 1 from alpha, this is 1 from alpha, and this is again A alpha, P alpha. It obviously gives you the same thing. One operates on the other. So there is a duality, and that duality we will note by the following way. One operation, one form operation on A I can write now this way, which is equivalent to A operating on P. So this is something that we may use later. That's why I wrote it down here. Transformation rules, very important things. As we said also, that sometimes this is how we will define one forms or vectors. Let me tell you one thing which I forgot to mention. Let me point it out here, that these are also sometimes called covariant components. Which are written with the downstairs indices. Okay, so transformation rules. Let's write for A alpha prime is lambda alpha prime beta A beta, and for the one form components it is the other way. One thing we need to remember, which you saw last time, is that lambda alpha prime beta comes from this, the chain rule of partial differentiation, and this is equals to these. One thing again we must remember here is that, so let me put it here, in case of space rotation, which is the normal rotation xy type, and space-time rotation, which are like Lorentz transformation, the transformation rules are same everywhere for the entire reference system or for the entire coordinate system. It doesn't depend on x alpha. Now this is always true for Lorentz transformation, which is a space-time rotation. This is always true for mutually inertial reference frames, which means that it is always true for special relativity. But in general, this may not be true, and we'll see that for general relativity, this will not be true. So in general, this is not necessary. This is something that we must remember. Okay, so let's come to metrics and scalar product. So metric, this will be the single most important quantity when we will do general relativity. So it's a tensor of this type 0 to. We write any tensor with a bar above. So this is the tensor. Because it is 0 to, it takes two vectors as input. So if the vectors are A and B, takes them as input and it gives a scalar which is the scalar A alpha, B beta, G alpha beta. What are G alpha beta? That you get by putting in the alpha and beta vectors in it. So this is essentially G alpha beta. This also we write as A dot B, and just we have used the notation, we will also write this as AB. And in this, one has to be one form, one has to be a vector. Now, what metric is, we also saw that metric maps a vector to a one form which is that if you put in a vector A here and just the other you put the beta unit vector, then what it becomes is, if you work it out, so it will be A alpha G alpha beta, which is the beta component of the one form. Right? And we also have seen, so this we have also called this operation as the lowering operation done by the metric. And we have the inverse of the metric, which we called, which is G again, but alpha beta upstairs. And then the raising operation is something that maps a one form to a vector. So G alpha beta, so it maps a one form to a vector. If I give it a one form, which is A beta, this will give me A alpha, which is a component of a vector. So now this is the component of one form, and this is the component of vector. So this index wise, these are essentially raising and lowering operations. So you raise the index from downstairs to upstairs or upstairs to downstairs. Basically, you go from the space of the vectors to the space of the one forms, or the space of the one forms to the space of the vectors. That is going from one's space to its dual space, essentially. Alright, the next stop for us, which you have learned, will be about the derivatives. So we learned how to do derivatives of tensors or components of it. So for example, we talked about this type of derivatives, which we even invented a shorthand notation, which is you write a alpha and then comma beta. That essentially means what is in the left hand side, and you can have that with the components of vectors also. I can take the derivative of the vector with respect to a scalar. Say the scalar is lambda. Well, in that case, I have just written the derivative of the component of a one form with respect to a scalar. You can do it as well with a vector. So let's do it a vector. That's more meaningful. So let's do it with a vector. So the vector is A. So this is essentially the scalar. Remember that the scalar is something which will parameterize the coordinate components. So if I write A explicitly, A alpha, it's a function of all the coordinates. So let me write the index mu over there. And then I've taken the alpha component, so I should have the alpha unit vector. So this is what it means, this differentiation. And then what we have done so far, E alpha is not a function of coordinates. So they cannot be functions of lambda because coordinates are the ones which are functions of lambda. E alpha is same everywhere. It doesn't matter if you change your parameter lambda. So here just let me remind you again that the x mu's depends on lambda. They are functions of lambda. So this is that becomes del, if I use chain rule now, del x beta, del x beta, del lambda, and E alpha just comes out of the differentiation because they're constants, at least for whatever we have done so far. And if lambda is the proper time tau, then what this becomes, that is del A del tau, is the first thing is the familiar A alpha comma beta. Del x beta del tau by definition is the velocity for vector, and then E alpha. So that too is the derivative of a vector with respect to a scalar that you have learned. And then a few special derivatives. Let me just remind you that del x alpha, del x beta, well, they are partial derivatives, the coordinates are independent. So this will only be non-zero if alpha equals to beta, which means this will be the Kronecker delta alpha beta. And we have just seen a little while ago, if I have del x alpha prime, which is a new coordinate system, this is essentially the transformation rule, so which we are writing as alpha prime beta. And what else we have seen? We have also seen that d phi, where phi is a scalar, this we could write as the one form taking the vector x. This also we have seen. So just remember, components of d phi are del phi del x alpha. These are one forms. So this is about the derivatives. And the last thing before we start our discussion today, you see that a pre-discussion has become a little longer today, but it is important. That's why we are doing it. So let's say tensors in general. So we write them as say mn x m vectors, m1 forms and n vectors as input and the output is a scalar. Right? Example we'll take, let's say, an example of this type of a tensor. So it will take one form and it will take two vectors. Okay, let's call this T because it's a tensor. So T, let's say it takes one form, so we'll write the one forms first. So let's say the one form is the unit one form, the alpha-th unit one form, and in between the one forms and the vectors, I put the semicolon sign. So say it takes the beta-th unit vector and the gamma-th unit vector. This essentially is the alpha, beta, gamma component of T. And that will have alpha upstairs and beta, gamma downstairs. Remember, if it was a one form, it will take a vector. So I will not have W alpha, I will say not have E gamma. I'll take only E beta as input and it will give me T beta as the component. Right? Now, how do I write it in terms of its components? Remember that I can write it in terms of its components. Components are T alpha, beta, gamma. And now I will need a basis for this complicated 1-2 vector, but that I can construct from the basis of what I have in one forms and vectors. So I will need a basis one form which is beta, which will come with this, component will be this index, and then outer product with gamma, and then outer product with a vector which is alpha. The index corresponds to the vector, stays upstairs. Index corresponds to the one forms, stays downstairs. And again, let me remind you with the old notation, this is the contravariant index. And these are the covariant index. Okay. Now it does matter which way I put this beta and gamma. This thing, T gamma beta, alpha beta gamma, may be not symmetric about the indices beta and gamma, So it does matter where I put in. Should I put in the vector in the second slot of for the vectors or for the first slot for the vectors? That will give me different results. Now, if I have this, and what I do is I don't put in anything here. I put in a vector here, and again I leave the third place empty. So this dashed are for empty. So what will this be? So this is beta gamma. I put in nothing in the first place, but I am putting a vector in the second place, which is for the beta. So this will be delta beta, and I have put in the vector A there, and then I will have. And once I have put in these things in the slot, obviously that outer product disappears because this will now become a number. This will become a scalar. That is what a tensor do. So what is this? This is T alpha beta gamma. The one form W tilde beta will bring out the beta component of the vector A. So I will be left with this. And you will agree that this is a tensor now, which has one slot for a one form and one slot for a vector. So this is a tensor of type 1, 1. So what I have done, I have constructed a tensor of type 1, 1 from a tensor of type 2, 1. And for that, what I had to do is, 1, 2. So I had this 1, 2 tensor, which I have made a product with a 1, 0 tensor. And this has reduced 1 from the 2, and that has given me a 1, 1 tensor. This method, this phenomena is also called contraction. I've contracted the index beta, if you wish. Okay, so it's this much of recapitulation, which is quite a bit of the part of today's lecture. Let us come to a discussion on curvilinear coordinates. So when I say curvilinear coordinates, I mean that I am in a coordinate system where the basis vectors can change with positions. So this is what I mean by a curvilinear coordinate. Now, for the time being, it is just of complete mathematical importance. We'll see how it comes to when we go to general relativity. One example of this is the polar coordinates, which is obviously different places, the basis vectors are different. The question is, how do we define a metric, or what are the things which changes and what are the things doesn't changes? We define metrics still like G alpha beta we get by inserting the alpha-ith unit vector in the metric and the beta-ith unit vector in the metric. These are the basis vectors of the curvilinear coordinates. This also, if you wish, you can write this as E alpha dot E beta. That is our definition of dot product. But you see that E alpha, E beta changes different at different places, which means the metric can depend on coordinate also. Just because E alpha and E beta depends on the coordinate system or where you are in the coordinate, the metric will also now depend on where you are in the coordinate. So this will not be constant case, constant metric, just we have seen for special relativity, it will be different. What about the coordinate transformations? For the coordinate transformation, again, the transformation rules can change at different places in the coordinate. So let us write this for vectors and one forms. This will look exactly the same, but now we will try to write it, or we should write it in terms of the partial derivatives, because that is more general than just writing the lambda, which usually is reserved for the Lorentz transformation. This is for the vectors components. If I have the alpha-th or alpha prime-th basis vector, remember when I am writing this, I am actually writing it for 4 components of it. The primed coordinate comes downstairs, this, and one forms. See, when we know how things changes for the basis vectors and the basis one forms, I can generate changes for any tensor, because the basis vectors for any tensor I can just get by taking the outer product of the basis vectors and the basis one forms. So this is del x beta now primed come downstairs, and so this is W, not E. Basis one forms. The prime comes upstairs in the transformation rule. These. So let me again remind you, all transformation rules are different at different x alpha, at different points in your coordinate system. Also remember that your basis vectors are different at different points in your coordinate system. And that will change a lot when you come to the derivative of a vector. So let's go there. Let's try to figure out now how the derivative of a vector look like. And this will have to go a little bit slowly, because this is something again which will give us passage to general relativity. Derivative of a vector now in curvilinear coordinate. So the vector is A, and say I am taking the derivative with respect to the alpha-th coordinate. And as we know that this is del x alpha, A I can write in terms of its components. I should not write alpha because this the alpha in the with the x in the denominator can be any component, not necessarily the vector component which I am taking derivative. There is a sum over the vector components with the basis vectors, which should have a different index because that index is summed over only with the component of the basis vector. This we have discussed earlier also, but I just wanted to tell you again. So what is this? So now this is the familiar thing will be there, E beta constant. But now I will have another term because E beta can change with X alpha. That's what we have been saying for this type of coordinate system. In general cases, this can change with X alpha. So I should have this term. This term is non-zero. So this is coming, let me write explicitly that this term is coming because basis vectors can change with coordinates, so which is X alpha. So when I write X alpha with a second bracket or curly braces, this essentially means that it's a set of all 4 coordinates. But yes, so E beta changes with all coordinates. So let us examine this quantity del E beta. Let's examine this. What is this quantity? Okay. The change is taken with respect to X alpha. So change with alpha component of coordinate. The changes of a basis vector, this is the changes of the bth basis vector. So change of betath basis vector. And when I write vector, I put an underline sign in it, not because it's a vector, but we have to remember that this has the components in d dimension. So we are talking about change in d things for the bth basis vector with respect to the alpha-th coordinate system. So it's not so very straightforward quantity to look at. So we have 4 such alpha, beta. If we fix, these are 4 functions. One for each component of E. And I said 4, but let me, because we wrote D just above, so these are D functions in that sense. D equals to 4, obviously, if you're talking about space-time. So this quantity will write in the following way. We'll write del E beta del X alpha as let me write it down and then we'll explain to you what it means. I'll write it this way. Now this we can always do. So we can always write it this way. So this is the component of the derivative along the muth direction. Beta is change of which basis vector we are looking at? And this is change with respect to which coordinate? Okay. So this has a name. It's called Christoffel symbol. We'll discuss about it later. Okay. Now I can use this Christoffel symbol to write my derivative. And if I write my derivative using the Christoffel symbol, then del A del x alpha becomes, the first term is A beta comma alpha E beta, and the second term now becomes, let's look at what was the second term. It was A beta del E beta del x alpha. So I'll have A beta comma mu beta alpha and E mu. But then you see in the second term, both mu and beta are summed over. It appears once upstairs, one downstairs. And when something is summed over, it doesn't matter what I write for it. So I can actually interchange the beta and mu. So I can write this as A beta alpha. If I interchange beta and mu, so this A becomes mu, and here I get beta. This will be mu alpha, and you see that E beta is common to both sides. The left hand side, just like before, we like to write A beta comma alpha and then E beta, but obviously it is not same as this because of this extra term, so I put a semicolon over here. Now this derivative is called covariant derivative. We'll see its importance later. But we understand now, if my coordinate basis changes with coordinates, then I can write, so this I can write this in component form, say, okay, so this will be of much importance for us. So let me put it in a box. What is the mathematical nature of this? Okay, so you see, this has one index upstairs, one index downstairs. So I can, so if I call it, if I define a tensor K, which takes dx one form and v as input. Now this tensor K is nothing but the covariant derivative thing. So it will be del v vector del x alpha. And remember that dx are nothing but w. So I can put in w beta, say for example, here. So what will this give me? This will give me v, if I write v in its components form, it will be v gamma semicolon alpha and then e gamma eating up w beta. So that is essentially v beta gamma, v beta alpha. You see, E gamma eating up W beta is delta beta gamma. So that makes this gamma to beta. So this is a tensor of type 1, 1. We can, so this is derivative of the beta component of a vector with respect to alpha. If we want to calculate the divergence, and in this sense, this will be covariant divergence. The simplest way to do it is that you write this beta and alpha, but you don't want this beta to be also alpha, then only it will become divergence. So you multiply it with or contract it with a Kronecker delta. So this is essentially A alpha semicolon alpha. And just using the definition of the covariant derivative, you can now basically put alpha in place of beta everywhere. So you get this. So this is the definition of the covariant divergence. And you can see it's a scalar. What about derivatives of one forms? So let's try the last thing today is the derivatives of one form. So you have seen the derivatives of vectors. So covariant derivatives, so we'll call derivatives in general, of one forms now. To do this, we identify this thing that if I have a one form P and it's operating on a vector V, to do this, we identify that if I have a one form P operating on a vector A, this is essentially, I have also written it this way, and this is a scalar. It's called phi, right? And if I write in component notations, this will be phi equals, say, p beta a beta. Okay. So let's take a derivative of phi with respect to coordinate. So let's do it here. So say del alpha of phi. This will means del alpha of p beta a beta. Let's work it out. Del alpha of p beta, keeping a beta out of the harm of del alpha, plus p beta of del alpha of a beta, which now I write as del alpha p beta a beta, let's say p beta, and let's write this in terms of its covariant derivative. So if you remember, this will be beta in its covariant derivative, and now I have to take out the effect with the Christoffel symbol. So a mu beta mu alpha. Now we do the similar trick we did before. So what we do is, I put this square bracket here. So I take del alpha p beta, and I want to write this term first. But then again we see that I have a sum over beta and a sum over mu. I can interchange them, and I can write this sum over, I can write with p, I can write the index mu, then this will be mu, and now this will become alpha. And as this downstairs mu becomes beta, my a mu also becomes beta, so that I can take outside with that a beta. So it is this. Please try the combinatorics by yourself. That's how we will learn. Okay. So this is what we have got. So let's stare at it for a little while and do some counts. So this is a one form of type 01, or tensor of type 01, which is a one form. This is a vector which is 10 type. Covariant derivative gives you a tensor. This is 1 and this the one form p beta is 01 type. So this entire thing is 01 type. So 01 here, 01 here. This entire thing, whatever it is here, let me write it here, say A, B type, should be such that the entire thing comes out to be 01. How do I do that? I can do that if this is a 02 type tensor. If this is a 02 type tensor, you see there will be a contraction of this 2 with this 1, so that will make this downstairs 1, so it will become a 01 type. So this tensor we define to be the covariant derivative of the one form. So how will I write it? I'll write it as P beta semicolon alpha. This I define as P beta comma alpha, which is the normal derivative. Now a minus sign with P mu gamma mu beta alpha. So let me just for contrast write for the vector here plus okay. So we'll stop here today. We have learned how to do differentiations with curvilinear coordinates just from complete mathematical importance so far. We'll learn a little bit about uh, derivatives of higher rank tensors, which we'll just write down from here. And then we'll learn a little bit about the Christoffel symbol in the next class. Thank you.